about some examples of vector spaces. Anytime we have Rn, we are just going to accept that as a vector space. Although I can spend some time proving everything, but those 8 properties were basically obtained from looking at this, so it's obviously a vector space. And also C and so complex numbers, you can take coordinates, n-dimensional complex numbers, and that's going to form a vector space. So this one will be a vector space over C. Although you can also think of this as like a 2n-dimensional vector space over R. Okay, so C over R. Okay, now for this one, let's try to prove Y. Okay, so prove Y C is a vector space over. Let's try to prove it. Well, I'm thinking of elements in C as vectors and R as a scalar. Okay, and therefore things in here are of this form, right? Anything that's a complex number, it's like a real number plus another real number times I, where A, B is in R, right? So that's something that we know to be true. Now, but we can also say since C is a field, and that's another thing that we're not going to prove, we'll just accept that that's true. C with the plus is an abelian group. By writing this, we don't have to check four properties like I mean, if you were to actually prove this, then we have to show something like, don't write this in your notes, but it would be like A plus BI plus C plus DI plus E plus FI is equal to A plus BI C plus DI, E plus Fi. That would be associativity of the addition, right? Yeah. And then 0 definitely belongs in C as well. And then A plus BI and then negative A, negative BI. These two are additive inverses, so they get 0. So all the properties that we expect for the first 4 properties of a vector space is ultimately true because C is a field, and being a field means that it should be a abelian group under addition, and C minus 0 should be a abelian group under multiplication, and there should be distributed property. All that's true, so this we don't need to check, okay? So that's okay. That means we just have to check the other 4 properties, which are 1 is the multiplicative identity in R, so I have to think about how this operates. It's just A plus BI, so that the 5th property, 5th and 6th property is it's multiplication by a real number is group action. So there's this action of the identity, and there's the action of identity. And identity element. And then there's a compatibility condition, which is like if you have A times B, and then there's a C plus DI. So I'm thinking of C plus DI as some arbitrary element in C. And this is definitely the same as this is ABC plus ABDI by the usual multiplication rule in complex numbers, but then you can rewrite this as A times B times C plus DI. So this says the scalar multiplication is compatible. So compatibility. Of scalar multiplication. And so that's done. And then lastly, distributed property. Would be that you have some real number times sum of two complex numbers. So you have one complex number plus another complex number. And that's equal to A times B plus A times CI plus A times D plus A times EI. So if you just use the usual rule for addition and multiplication and distributive property in C, you get this. But you can rewrite this as A times B plus CI plus A times D plus EI. So that says the distributive property is true. Now, if I write this, you might be confused in what I'm trying to do here. Like, what am I proving? Well, think about how the distributive property was written. If you go back and see the distributive property, it's written like this. Some constant from the base field is multiplied to two vectors u and v, and that has to equal to c times u, c times v. That's the property we're trying to show, right? How do you show something's equal to something? Well, you say this is equal to another thing, it's equal to another thing. You gradually transform until you get here. Okay? So in this context, C, instead of C, let's just choose A for the real number. And because U and V are the vectors, we're thinking of C as a vector space, so we have to choose U and V from C. What are elements in C? C is complex number, so instead of U, I'm going to put B plus CI, and then D plus EI. Those are the two complex numbers. These are just generally two complex numbers, right? And then you just do the calculation, and of course I'm kind of like skipping steps here because because addition is associative, you should first get rid of the parenthesis. And then you can multiply A to every one of these to get this. Okay. But then over here and here for here I can factor the A out, for here I can also factor the A out. And this equal to this is exactly this form, where U is this and V is that. Okay? Yeah. All right, so whenever you're tasked to show that such and such is a vector space, then you have to check all 8 properties, which means you have to remember all the 8 properties. And some of them you might be able to wiggle out of having to write all of the proofs by stating something that's obvious, but in other cases you have to show that something is equal to something. Just like here, I'm showing A times B times U is equal to A times BU. This is what I want. But to go from here to there, the obvious step is to use this multiplied to each individual one. There's another thing I want to say. A lot of times, proofs look the beginning and end. How many of you like solving mazes when you're a little kid? You remember solving mazes, right? How do you solve a maze? If you just start from the beginning, that's a novice. You haven't played maze that much. If you played harder maze, you always have to start from the beginning and also start from the end. And at some point, you're going to meet in the middle, right? That's how you solve a maze. Harder mazes are always solved that way. So same thing here. You just write down what you're trying to prove, and think about what these are in this specific context, and think about what should be proved. So you write this as like C times B plus CI plus C times D plus EI. Okay? And when I wrote this, I wasn't looking at this, I was looking at this right side with the idea that U has to be this and V has to be this. And all I did was I just rewrote this in that form, and I rewrote this in this form. And then I realized, oh, so in this context, what I need to show is this identity, that this side is same as that, right? If I want to show that these two sides are equal, then there must be something in the middle. What could that be? Like, I'm just pretending that I'm calculating this in C. Just multiply things out. And then, if you have this, then can you make this into this form? Because you know what has to be the conclusion. You look forward to this and think about how this could be this. Well, obvious choice would be factor the A out, factor the A out. Therefore, this is true, and the proof is that. Is that okay? Yeah. Sometimes the reasoning seems a bit circular, but you have to be cautious of where to begin, where to end, and then you have to try to fill in the middle somehow. Okay? And there's the other way, right? The other way is when you have A plus B times C plus DI. So these are the two scalars, and this is one vector. And I'm really thinking of this rule. A plus B times U equals to AU plus BU. Right? So in order to show this, since my U is this guy, we're trying to show, what are we trying to show? We want to show that A C plus DI plus B C plus DI is what's needed, right? I went too far to the right. Right again. A C plus DI plus B C plus DI is what's needed. That would be exactly corresponding to what I want to prove here. And you know, when you write proofs, you sometimes want to look smart, so you erase what you were thinking. Okay, yeah. That's what throws off a lot of people. All these textbooks are written by smart people, and they would like on the corner write all kinds of things that's needed, and then later they erase, and you have no idea where this proof came from. Okay, but this is what I need to prove, and how would you prove it? Well, just FOIL, right? So you have AC plus ADI plus BC plus BDI. And then now you ask, is this same as that? Well, of course, right? A, you factor the A out, you factor the B out. So that's true, so you're done. Okay, so that's the proof. And this is 1, 2, 3, 4. This is 4 properties. So we've proved all 8 properties and we're done. Okay. All right, so that's the proof. What's another example? Okay, so let's think about f infinity. What does this mean? Oh, what does R3 mean? R3 means R product with itself 3 times. And this is a set theoretical notation of collection of tuples or tuples made from each of these elements. So this means you have x, y, z, a tuple of three things, where each one of these are from R. That's what that means, okay? So knowing this, what would this mean? What would f infinity mean?
Just infinitely many fields.
Yeah, that would mean the tuple's length is infinity. So it's like A1, A2, A3, never ends, okay? So it's like a sequence of numbers. That's what it means. Well, if you have sequence of numbers, can you add 2 sequences? Yeah. So here the addition would mean the addition of one sequence plus another sequence can be written as A1 plus B1, just the usual vector addition that we know can be performed here, even if you have infinitely many things, right? How about scalar multiplication? Can you do scalar multiplication? Scalar multiplication would be if you have some constant multiplied to A1, A2, A3, da da da, it's simply C times A1, C times A2, C times A3, right? Again, exactly the same way you would do in R3. If you had the number outside, you would multiply it to individual ones. That's scalar multiplication, right? So we're doing the exact same thing. And of course, again, once you have defined these binary operations, you have to check 8 properties, right? Those 8 properties are going to take a long time, so I'm not going to do it, but it's pretty straightforward. So for example, what will be the additive identity here? What's the Everything 0. Yeah, that will be the additive identity. Definitely it's going to be an additive identity, right? And then what will be the additive inverse? Well, it will be everything with minuses in front, right? Okay. Yeah. How about multiplying by 1? It doesn't do anything, right? So that portion, group action by identity, is true. And then if you have 8 times b times this, it's the same as a outside and b inside, and then multiplying a later. So that compatibility condition is true, and then you can also check distributive property. So it just takes too long to write them down, but it's pretty straightforward to show that this is a vector space. Okay, number 4. Okay, that's a very strange notation here. So S is a set, F is some field, and this means it's a set of all functions from S to F. And that's a vector space. Now for this fourth example, I want to take a moment to explain this notation. Now I believe in your previous course named MAT 200 you learned such a notation. How many of you remember such a thing? Anyone? Maybe? 2 people? Vaguely. Okay. So let's try to decipher this notation before we try to prove that this is a vector space. So just think of a simple case. Let's not even bother putting a field here. We'll just think of A as, say, 1, 2, 3. No, I don't want one. A, B, C. So letters A, B, C. Okay, and B as, say, 1 and 2. And we want to think of A to the bth power. What is this object? What does that mean? Well, consider a function from B to A. So I'm claiming that this is the ideal notation for all the possible functions from B to A. Okay? Can you give me one example of a function from B to A? 1 goes to? Come on, A, okay. 2 goes to? B. And C, there's nothing there. That's an example, right? Yeah. And that's a graphical notation, but this can be written as just simply AB. So that the first component will give you the value for 1. The second component will give you the value for 2. Okay, let's see if you understood it. What if I have a function that's like, it sends 1 to C and 2 to A. Okay, how do you represent it as a tuple? C comma A, right? C comma A. Right? So now if you think about all the possible functions from B to A, they'll always look like something comma something, right? Right? Because you put anything in these two, like for example, if you put B, B, what does that mean? That means f of 1 is B and f of 2 is also B. Right? So you do that, and then x and y are both from A. Okay? That would be identical to, well, I have to be careful saying identical, isomorphic to set of all functions, f function. Alright? And therefore you can kind of see that, oh, it's like so it's like set of all functions is, we say, isomorphic to A cross A, right? Because A cross A is like tuple of elements from A, right? But we kind of know that it's a bit different from A cross A, because if you have this f itself, you're really putting a parameter here. We're putting 1 as a parameter for this A, and the second guy corresponds to the value of 2, right? So it's like you're taking, so it's something like this, r cubed, except instead of just putting r, the same copies of r, you parameterize each r by element of the base, element of the exponent. Okay, element of the exponent parameterizes each individual copies of the base. Okay, and that's why you have this notation. See, if you have a function from s to f, and if s is like 1 and 2, right? In that case, if this is size 2, this is isomorphic to f squared. That's why you have this notation. If you have like 1, 2, 3, 4 value, 4 as your s, then this space will be isomorphic to f to the 4th power. Yeah. However, we don't want to say it's just exactly like this, because here, not only can you go with a finite set for s, you can even choose infinite set. So the interval 0 to 1. How many real numbers are in the interval 0 to 1? How many do you have? How many real numbers are in 0 to 1? Infinitely many, right? There's 0 and 0.1, 0.123. You can think of all decimal numbers that belong to it. This is infinite set, okay? And you can even talk about like that. And this would be an example of such, where we're talking about all the functions from 0, 1 to f. Okay? All right, so if you have such a thing, then this is also a vector space. Now, why is this a vector space? Well, let's think about this as a vector space. Oh, give me an example of a function that's defined from 0 to 1, and it's a real values function. Let's just think of this f as r or c. Oh, by the way, in this class, whenever I write f, I'm trying to think of this as either r or c. Instead of writing r or c, it's easier to just write f once. Okay? So, give me a function that's defined from 0 to 1 that gives you real value. F of x, what? Give me a function.
Yeah, x squared.
X squared, good. Give me another function.
X cubed.
X cubed. Now, if you add these two, is that again defined on 0 to 1? Yeah, right? It's again a function that's defined from 0 to 1. So, this space, you can add two functions to get another function. Can you multiply anything to f of x? So, f of x plus g of x definitely belongs to f(0,1). But not only that, can you multiply anything to this function? Yeah, anything times x squared is again a function over 0 to 1, so that also belongs to this. So you can see that, again, you can do addition and scalar multiplication, and that turns this into a vector space. And this is in line with my previous discussion. We were talking about audio signals being vector spaces, right? What's an audio signal? It's a function over an interval, right? If you have a 4-minute audio, your favorite music, right? Well, you might think that's artwork you can't convert to math, but unfortunately mathematicians can do that, right? We can convert it to math. How? Just record all the amplitudes of the wave at each time for every moment between 0 minutes to 4 minutes. And that gives you a function, right? But because that's a function, you collect all possible music that's been made or to be made or it will never be made. If you collect all the possible music, then that's going to form a vector space, because you can add to audio signals, you can amplify audio signals. So once you have the vector space, then you can play on it, like all the things like finding a basis, transformation, and all these different things, okay?